Hello everyone. So today we will be starting with a new chapter that is electricity. And electricity, we call it as a form of energy, right? It is nothing but a form of energy, right? So this form of energy is widely used, and why it is usually widely used because of the reason of interconvertibility. In interconvertibility means that you need energy in different forms. You also need heat energy, right? You also need light energy. You sometimes need sound energy, that is the speakers and all, right? And sometimes you need mechanical energy also, like fan, where there is a rotating part, right? And many other forms of energy also. So many forms you can consider here, like, so this type of energy we required, right? Heat energy, light energy, sound energy, mechanical energy. The different devices which we are using in our home require this form of energy. And we know that energy can neither be created nor be destroyed. That is, it can be only transferred from one form to another, which is the law of conservation of energy. So keeping that in mind, due to this interconvertibility is very easier, right? So interconvertibility of electricity is easier. So that is why this energy is used as the primary energy form, right? So electricity or electrical energy is used as the primary form of energy, and then the devices which we are using, we use this electricity to convert into different forms of energy which we require, such as a fan here, such as a speaker here, right? Such as LEDs here, such as heat energy required here, such as heater, toasters, and etc. So this electricity, we find that this form of energy is easier to convert into these form of energy. So this is used as the primary form of energy, and that is why in our home we receive energy in the form of electricity, and we use this electricity, and our devices use this electricity and convert into different forms. So that is about electricity. Now, electricity is all associated with the moving of charges. First of all, before going into electricity and electric current, we must understand what is a charge. And already you might have known that charges are what? It is a property. It is the property due to which electric forces occur. Right. So this is the reason why electric forces are occurring. You know that charges are of two types. Let us go into the fundamental level, right? If you know, everything is made up of atoms, right? Everything at the fundamental unit, as you say, it is nothing but the atom. So atom is, you know that it is like this only, right? You know the construction of atom. You know the construction of atom. It is like this, right? So these are your, let us say, this is your nucleus. Let me draw it in the center only, right? So this kind of structure you are having for atom. So this part is known as your nucleus. You know this, and this comprises of proton and neutron, which is most of the mass resides in the nucleus only. And we have electrons which are revolving in these orbitals. So these are nothing but electrons. So these shells are nothing but we call these shells, or these are different energy levels actually. So on these different energy levels, different electrons are revolving around this nucleus. So most of the mass in the nucleus. Now, if you consider and at a normal state, this atom exists as a neutral, right? It is neutral, or more appropriately, we call it as electrically neutral. Electrically neutral because The number of protons, the number of proton if I represent by this, right? Number of protons is equal to electrons, right? So what happens to electrically, this atom is neutral. But now let us consider the case, suppose this is electrically neutral case. Now what happens? Let us consider a glass rod, which we have already studied. Let me go that into much deeper, right? This is glass rod, right? And then you are having a silk cloth. So this is your silk cloth. And when you try to rub this, right? When you try to rub it on the silk cloth, what are you doing? You are rubbing this, so you are giving, there is a frictional energy is there, right? You are putting this glass rod, rubbing it on the silk cloth, so there is a temperature increase, right? There is a momentarily temperature increase. So due to this increase in temperature, what happens? This was the, let us say, atom of glass, right? This is your nucleus, and this is your, let us consider these are your energy levels, and this is the electrons, right? So let us consider that this is your electron is revolving here. So now due to this rubbing, what happens? This electron will get loose. It will lose. So what happens? Now you can see that protons become greater than electron because this atom has lost one electron due to this rubbing. So what happens? Protons dominate, and you know that a proton is a positively charged and electron is negatively charged. So what happens? A positive charge will be existing. That is, this glass rod becomes positively charged after rubbing. Why it has become positively charged? Because it has lost electrons, and now the positive charge will dominate this. So what happens now when you bring this to a neutral body, right? Close to a neutral body. Let us suppose this is a neutral object. So this neutral object you are bringing closer. What happens on this neutral object if you bring this charged glass rod, positively charged glass rod? What happens? You know that since this positive charge is closer and this is electrically neutral, what will happen? Due to this positive charge, the positive charge will attract negative charge. So there will be attraction between these two, right? So due to this attraction, what will happen? This object will start to become polarized partially. What will happen? Negative charges will be coming closer to this positive, to this glass rod. And what will happen? Since this positive charge is repelling the positive charge, so in this neutral object, positive charge will be get repelled. It will go on the other side. So what will happen? Due to this partial attraction, force of attraction will be observed, right? So that is how what is happening now. Since the electron was removed, after the removal of electron, there is not a motion of charge. There is no electron moving. There is no proton moving. Everything is stationary. That is why at the time of this time we call it as the electrostatic force. What we call it as? We call it as electrostatic force. We call it as electrostatic force. Why electrostatic? Because this glass rod was positively charged and other object negative charge come closer to the side where the positive where the glass rod was being closer to the object. So now there are charges at rest but the force exists. So that is why that force we call it as electrostatic force. And everything we study under this condition, that is called as electrostatics. But now what happens? We are talking of electricity. We are talking about electricity. So electricity is nothing but we are now considered with the motion of charges, right? Now we will be seeing a different type of phenomena of charges where charges are moving, right? And when these charges are moving, that means they have a speed, right? With certain speed they are moving, right, from one place to another. And this motion of charge or the rate of change of charge, we call it as electric current. Electric currents. So what is a water current? When in a stream, you call that when the molecules of water are flowing, the water is flowing, that is the water molecules are moving from one place to another, you call it as water current, right? The current of water is very strong. The current of water is water currents. And in power and hydropower plants, we have a factor of this water current also, how much strong the water current, at what height the water is, and accordingly the water current will be. So this water current is what, on an whole I want to say is that water current means that there is motion of water molecules. Here when the charges are moving, we call it as electric current, right? So rate of change of charge is nothing but your electric current. Now mathematically, if I want to call this, we call that rate of change of displacement with respect to time, we call it as velocity. Similarly, we need a formula here. The formula is the rate of change of charge with respect to time. So charge we denote it by q, this is denoted by q. If it is positive charge, we call plus q. If it is negative charge, we call it as minus q, right? Negative charge is generally it is electron, and positive charge, so this is the fundamental unit of charge, that is electron. So now q is represented as a charge, and t is your time, right? So what is the rate of change of charge is, right, we call it as suppose at second position the charge was q2, the first position at charge was q2 at t2 time, and we are seeing at time. So that is nothing but your current, which is represented by I, right? I or small I sometimes for AC, right? You need to know that the current is represented by I. Okay. So this is all about electric current. So electric current, let me write it down for you again. So that is I is nothing but the change in Q by change in time, right? And you know that the unit of Q charge is coulombs, right? This is the unit of charge. This is nothing but coulomb, right? And time unit, you know it as second. So what will be the unit of I here? It is nothing but coulomb second inverse, or coulomb per second. So this coulomb per second, right? This is also called as a unit, SI unit, which is called ampere, right? So what is the unit of current? So unit of electric current is what? Amperes, and it is represented by capital A, and symbol for electric current is what? I, right? So this is nothing but your electric current. And what will you now call, let us say 1 ampere current? So 1 ampere current, because in exams questions are asked like this, define 1 ampere current. So it is what? When 1 coulomb of charge passes through a given cross section in unit time, that is 1 coulomb in 1 second, is called as 1 coulomb per second, or 1 ampere. So this is nothing but your electric current. So this electric current is actually flowing, and then it is converted into some other kinds of energy, right, as required by us. So that is why this electric current we receive as the primary form of energy, and then this electric current is converted, or electricity is converted into some other forms, right? And because why we are using this electricity at home as the primary source of energy, because there is a reason. The electricity generation, the generation of electricity generation is somewhat not that difficult when you uh, compare it with other forms of energy, right? And then it is transmission, that is the transferring this power, or electrical power or electrical energy from one place to another, is quite cheaper also. And then that is are that these are the some of the reasons why electricity is used, because you can produce this by what? Wind power also, because we know when turbines are rotating, that is when windmills are rotating, it is connected to dynamo, then we are generating energy. Then there are hydro plants also, where dams are created and we generate electricity from water. Then there is the most widely part of where the electricity is generated, that is thermal plants, that is coal is burnt to generate steam, and that steam will run the turbine, and ultimately the generator will run and generate electricity. So these are thermal plants. Then we have nuclear energy also. So there are so many forms by which we can generate energy, right? Some of them are also non-conventional sources like these, right? In this one more plant is like solar plant. Today nowadays solar plants are being widely used as generating for electricity in domestic houses also. Some people are putting solar panels to generate some ratio of power they are using by their on their own by using solar panels. So that is also non-conventional. So on and whole, it is very widely many methods are there to generate electricity. The transmission of this electrical energy is somewhat cheaper and easy, and that is why, as compared to other forms, it is not easy when you talk in like holistic terms. But yeah, if you use any other form of energy, it is much cheaper and much more practical, right? So that is why we use electricity as the primary source in our homes, and then we use this electricity to convert this energy into some as in whatever form we require, right? So this is why we are using electricity, and why what is electric current. So that is all about the electric current. Now let us move to the another discussion, which is the direction of current, right? Because this is a more confusing topic which I want to discuss. So what happened in earlier times? There were not a discovery of which electrons are moving or what is happening, right? That today we know that electrons move and then current is flowing. In earlier time, that is not the case. The electricity was assumed that suppose this is a cell, you know. Now let us talk about electric circuit also. You know that this is a cell, right? This is connected, and then we call that some light is there, some load is there, then we call it as resistance. For now, just assume that. Just follow what I am telling, because I will be discussing about resistance and this cell later on in detail. But for the moment, let us consider this. So you know this is positive terminal, negative terminal of a cell. Let us consider a pencil cell. The conventional direction of current, that is the since older times, we have assumed that the current flows from positive to negative terminal. It flows from positive to negative terminal. This is important, right? Of the cell, right? This is the conventional direction of current. But what is happening actually? The electrons motions are the motion or the movement of electron is in the opposite direction. Means that electrons are moving like this from negative terminals only. There is excess of electrons. So this is moving like this. But since from earlier times we have assumed that the conventional direction of current, or the older times we have assumed that the direction of current is positive to negative, still although we know that electrons are moving from negative to positive, we consider the direction of current as positive to negative terminal only, although the electrons are moving from negative to positive, right? So we know electrons are moving from negative to positive, but we consider the direction of current as positive to negative terminal only. Will be the direction of current, right? So this is all about your current, right? Now let us consider a example of let us say a stream, right? Here water is there, right? River is there, and suppose the river is flowing very slowly, right? Or it is the water is what? It is a stationary for a moment, right? Let us consider it is a stationary for a moment. Although in a river water is continuously flowing, but let us consider that the water is stationary for a moment, right? Now, suppose I want to move this water, although the natural force of flowing water is not there, but I want this water to move. What will I do? So somewhere I will put a pump here, right? Somewhere I will put a pump here, and then I will connect this pump into the river, inlet pipe of this pump to this river, and the outlet part I will leave it to the river also. So from now I will turn on the pump, and let us consider that the water starts to flow now. So when water was not flowing, what was responsible to make this flow of water possible? This pump. Okay. Because when there was no pump, the water was stationary. You can consider the simpler case to your overhead tank also, right? Let us consider the case of overhead tank. So this is your, let us consider this is your overhead tank, right? This is the overhead tank kept on the roof of your house, right? This is the overhead tank. Now this is at a height, and from down you have a pump, right? And through pipelines this pump is connected to this tank, right? When you turn on this pump, then only the water will flow up, right? So similar case you can consider in case of a electric charge. So suppose a charge is here, right? So you need to bring this charge to some other position, let us say at this position, x distance. Now this is the first position, P1 position, this is the P2 position, you want to bring this charge. So you need to do some amount of work as the pump was doing, right? The pump was doing some work to, or some energy was consumed, right? Or it must give some potential, it must have, water must have some potential, right? And similarly then only it will, you must give some energy to the water to, so that it reaches the top of the overhead tank. Similarly, in electric charge also we need some amount of energy, or some amount of work is to be done to move these charges, right? Some work is to be done in putting these charges into motion, right? So we need some work to be done so that the charges on their own they won't be moving, right? So that is why we call a term we define for this in electrical circuits is called as electric potential energy. Let us consider. So electric potential energy we call as that the amount of work done, amount of work done in moving a unit charge, right? Unit charge, right? So this is nothing but we call it as what? The work done is what? Nothing but energy. You know that work done unit is also joule and energy unit is also joule. So electrical potential energy is what? The amount of work done in moving a charge, right? And if the charge has a potential to move, right, then we call it as electric potential, right? Right. So electric potential energy is that the amount of work done in moving a unit charge, right, from one place to another, or to a place in the presence of electric field we call. Electric field, you can understand it as a region of where the electric forces on the charge will come into play, right? So electric potential is what we call it as the potential or the capability of an let us say to the capability of a charge to move. So this is defined as nothing but the work done upon charge. Okay, sometimes we represent by this capital Q also. So amount of work done in moving a unit charge, right? So this is what we call it as electric potential, right? So work done per unit charge. This is what? Work done per unit charge, right? Or the work done by the electron, right? Because this is the case, work can, if we are doing the work to move it, then we are giving that potential energy to that electron, right? Now on its own, if it has a potential energy, it can also have on its own, because Suppose initially there's some energy with the electron, so now it has the capability to move it on its own, and that capability, that is the work done per unit charge, we call it as the electric potential. So what we call this as, that the pump which I was talking about is nothing but electric potential. So this an electron or a charge must have in order for it to move, which is, what is electric potential? It is sometimes denoted by V also, and we call it as work done per unit charge, right? So the unit is always, you can see that the unit, if I talk about, the unit is what? Works unit is joule, and this unit is coulomb. So this unit is joule per coulomb or joule coulomb inverse. Or we call the unit of electric potential as volts, right? So we will define 1 volt as the electric potential when amount of work done is 1 joule in moving a 1 coulomb of, that is a unit charge. That is 1 joule per coulomb is nothing but your 1. So this is electric potential, and this is electric potential is given in the form of batteries or cell, right? So you know that electrons, now you need to consider conditions which are necessary for flow of electric current, right? So consider this, right? So conditions necessary, first of all, that potential is there, right? Suppose this is at x potential, the point, because at different points we are having a different electric potential in a circuit, if we talk, right, or in a path where electricity is flowing actually, and on that path we define that at every point some electric potential is there. So the condition is that when the electric potential, suppose that electric potential is V1 here, and at this point electric potential is V2. So when there is a potential difference, that is, first condition is that there must be electric potential difference, right? Because if suppose V2 minus V1, if I do, it is 0, then from this point to this point current will not flow, right? There some be electric potential difference, right? Suppose that is the same case. Suppose uh, an overhead tank is placed on the ground only, right? And here is the overhead tank, right? And what is if you are putting it on the roof, right, then you won't be observing only when you, in case when this tank is placed overhead, right? Only this clay, on this case when the tank is placed overhead, then what happens here? The potential energy, here the potential energy, because due to this height the potential energy is high here, and in the potential energy is low here. So there is a difference, there is, it is high, there is a low, then only this water flows, right? Then only this water will be flowing through this pipe. So same is the case here, right? There must be a electrical potential difference between these points, that if V2 minus V1 is not equal to 0, then in this case what will happen? Then in this case current will be flowing from higher potential to lower potential. Suppose V2 V1 is greater than V2, then current will be like V1 to V2, and this is the direction of current. Obviously I told you that this is the direction of current, that means electron is flowing up. So that is the meaning. So what I want to tell you is that the conditions which are necessary for the flow of electric current is that there must be electrical potential difference, and the second point is that there must be a closed path, or we call it as circuit or electric circuit. So these two conditions are necessary for electric current to flow. So we represent this all by using a circuit diagram. So what is necessary? Electric potential difference, and this is provided by batteries. or cells, right? So this is your battery, right? And then we are drawing wires like this. So these are nothing but we call these as wire. This is wires. So this is circuit diagram. And suppose we are having a bulb here, right? This is a symbol for a filament bulb. So we are having a bulb here. Now you can see that this path is closed. So this is positive terminal, this is negative terminal. Current will now flow because there is a potential difference and there is a closed path. This larger stick is represented as positive. That means this is at higher potential. This is lower potential. So there is a potential difference, right? And we call this as V. If suppose this potential difference is V1, this potential V2. So V1 minus V2 we call it as V only. So we don't represent this, we represent only directly it as V, right? So that is what we have. We are having electric potential difference between these 2 points, and we have a closed path also. So now the current will flow, and then this current will be flowing through this bulb and it will flow, right? And we represent also a switch like this. Let me tell you about symbols also. So this is now an open switch. This is open switch. Open switch means what? Open switch is what it is controlling your this part, that there must be a closed path. So switch is open, that means this circuit is now open. So this condition is not satisfied. So the current will not flow. That is why then this will turn off, right? The moment you close this, and the close switch is represented like this, right? This is a closed switch. So when you close this switch, what will happen? Now the circuit becomes closed and this bulb will become on. So these are the two necessary conditions which are responsible and which must be there for electric current to flow. Right? You know about electric potential, you know about electric potential and electric potential difference. Right? Now we will be talking about more in more detail. Suppose we have different materials, right? In some materials, the current passes easily, right? Current flows easily, right? Those materials we call it as conductors, right? And in which current doesn't flow easily, right? Doesn't flow at all, right? Then we call this as insulators. So in this the current won't flow, in this the current will flow. And to classify this into insulator and conductors, we have a property also, and that property distinguishes these conductors and insulator, and that we call it as resistance. So this will be now a beginning of Ohm's law and discussion of relation between voltage and current, right? So let us now discuss. Suppose this is let us say your bulb is connected, right? And then you have this potential difference. And then what you do? Let us consider that the cell is like that, the current is flowing. Okay, and the bulb is like this. Now what I do? Suppose at V1 current voltage was applied, the current observed was I1. Now what I will do, I will twice this voltage. Let us twice this voltage. How I will do? I will connect two of these cells, right? Like this. Now this becomes a battery. So I double this voltage. What will happen? The current will be doubled also, right? And let us see. Now let us see. I thrice in the voltage, the current also thrice in up. Okay. Then let us say I connected some another load in the place of this bulb. I connected some other thing and did the same thing. Suppose here it was V1, the current became 2I1. When the voltage was V1, the current was say 2I1. Then I increased the voltage to, let us say, 2V1. I got the current as 4I1. So 4V1, when it quadruple the voltage, the current becomes, let us say it became 8 times. So you can see, if you try to plot this on a graph, in this case if you plot this on a graph, let us say I am using this for current, this for voltage. So at I1 point the voltage was V1. The I2 point, the I2, that is 2I1 point. Let us, this is 2I1. So the voltage was also 2V1. And if I join these points, right, this is what the point. Then I join this, I will get a straight line. Here also, if I try to draw this graph, right, this is your I, this is your V. Here it was I1, let us say. Then the voltage, let us say this was uh, at 2I1, it was V1 only. And that at 4I1, it was V2 only. So like this. So in both the cases, I am observing a straight line, right? In a straight line. And you can see that as the current is, because straight line means was, this is a direct relation. That means the current is directly proportional to the voltage. That is the cause, that is the effect is directly proportional to the cause. The cause is the voltage, that is a potential difference, and the effect is what, the current. So the I is directly proportional to V, or if I can write this also, V is directly proportional to I because of a straight line. And when you know that if I try to remove this proportionality sign, because this is a straight line relation, that means if I multiply the current with something, a constant, if I multiply, then I will be getting the voltage. So that constant I represented by R, and this is what is called as the Ohm's law. So what happened when you are increasing the voltage and the load is kept constant, right, and the temperature is also same, the two conditions are necessary, that is the temperature isn't changing, right, and the load is also the same, right. In that case, if you are increasing the voltage, the current is also increasing in proportion. And if that proportion is R, that is uh, it is always something times of current is voltage, and that time is that multiplying factor is nothing but called as the resistance. What we call it as, it is called as nothing but resistance. Okay, resistance, what we call it as resistance. So let me discuss this about resistance. So this direct relation, this is called as Ohm's law. Ohm's law, because Ohms was a scientist who discovered this, right. So V is equals to IR, so this is nothing but Ohm's law, and this R is called as the resistance. So what is resistance? So it is the property, it is a property of a material to oppose the, okay, it is a property of a material to oppose the flow of current. We call this, why we call this, let us understand by this. Suppose if this resistance is high, okay, if resistance is very high, resistance is very high, okay, right. So that means to get a higher amount of current, if this is very high, right, suppose resistance is 2, right, the unit of resistance, first of all let me discuss the unit of resistance also, then I will tell you about the concept. So unit of resistance, so unit of resistance is nothing but, you can see from here also, R is equals to V by I, or you can write it as volts per ampere. And in order to honor this ohm, right, then the unit of resistance is also called as ohms. This volt per ampere is also called as ohms, and the symbol for this ohm is this omega, this, right. This is called as the ohms. Okay, now let us see the concept of how this resistance, why this is the property which is defining that it is the opposition to flow of current. So I know that V is equals to IR, right. Suppose the resistance of a load is, let us say, 2 ohm, right, and I want, let us say, 3 amperes of current to flow, right. I want 3 amperes of current to flow, suppose. So what must be the voltage applied? It must be 2 to 3, that is 6 volts. So what is voltage? It is the potential difference. That is the potential difference must be units of 6, that is 6 volts. And suppose I want now the time resistance is suppose 4 ohms, right? Or let us say, let us consider the inverse. Now let us consider that there is 4 ohms of resistance is there, right? And now I require 3 amperes of current. Okay, current is same. Here also I am want 3 amperes to flow. This is the circuit. So resistance is represented by this zigzag line, right? This is nothing but resistance. So this is the resistance. Now this becomes your electric circuit. This is connected to this voltage, and the current is like this. So I am telling that when the resistance was 2, the current I want is 3, suppose. Then I need to apply this potential difference as 6 volts. Now suppose the resistance is 4 ohms, and now I also want the current to be same, that is 3 amperes only. What will be the voltage? That is 12 volts. Now you see that I need a higher potential difference. Now this is higher, right? So I need a higher potential difference now to flow the same amount of current. Why? That is because the resistance is increased. That is the property to flow the opposition of charges. It is increased in this case, so I want more of the force to flow the electrons. So you might know that suppose a pipe is there, a plastic PVC or plastic pipe is there, right? Water is flowing in that, and you try to pinch this, right? What are you doing? You are actually increasing the resistance. So if more amount of water needs to be say flow, now the pressure should be increased to flow, and that is the same case is happening here, that if the resistance becomes larger, then the volt potential difference required is high. So in that way you can understand that this is the property which is opposing the flow of charges, because when this resistance is high, we need more of the potential difference to flow the same amount of current. This is 3 ampere, this is 3 ampere. We need if 3 amperes, then potential difference is increased due to this increased resistance. So that is why this is the property uh, which offers opposition to the flow of current. Right. So this is the case. Now further this, if we go further deep down, now we will consider about this resistance, and it depends on the material first of all, right? So material it depends on materials length also, and it depends on materials cross sectional area. So what do you mean by cross sectional area? I will tell you, right? Suppose there is a rod, this is not a wire. Let us consider this is a rod made of some material. Now the current will be flowing like this in this rod. Let us say current will flow like this. So what will be the cross sectional area? Cross sectional area of this rod is nothing but a circle. So when you cross section, that is cut from between, and then you see the section of it, it is nothing but a circle. So that is nothing but cross sectional area. So why we consider cross sectional area? Because there it will be the area where the charges are flowing through. So depending on size of this cross sectional area only, the flow of charges can be through that cross section only. That is why cross sectional area is a point of interest here. So material it depends on length and depends on cross sectional area. So material means what? Copper, suppose, which is the very good conductor of electricity. The best conductor is actually silver. Silver is the best conductor of electricity. Its resistance value should be, suppose, good conductors. Now you can understand that good conductors or the conductors will have resistance value very low. That is, the opposition will be offered very less. That is why the current will flow easily. That is, V by I is equals to R, you know. So what is the meaning? R is inversely proportional to I. So more is the resistance, less the current will flow through it. So that is why good conductors, that means the current flow will be easily very high. So that means the resistance of these conductors will be low. Insulators, conductors resistance will be high. So the copper is the best material, so its resistance is the lowest. But we are not using to construct wires. Why? Because this is expensive. And copper we are using, which is the second one after silver. So we use copper as the material for building wires. So as I told you that resistance depend on these three different factors, which is the material, which is the cross sectional area, and which is the your It is cross-sectional area, length and material. Also there is a factor of temperature also, right? But temperature we generally consider as constant, right? So that is why we are not bothered about this temperature, but on and all, if you are varying temperature, it will affect the further property of resistance. So that is how temperature will also affect resistance. But let us see, this resistance is directly proportional to length, first of all, right? That is, if the length is kept on increasing, right? If you are, suppose this is a L length, right? It is having R1, and suppose now you are using this L by 2, right? So here it is R1. So if it is, if the area, cross sectional area is same, here cross sectional area A also, let us say, here cross sectional area is A also. That is, though the thickness of this wire is same in both the cases, only the length of this wire is half. Then in this case, if this is the resistance of this, then this resistance will be half. That is, in direct proportional to length, resistance will be there, right? That you can verify with the different experiment also. The activities are given in your book where they are measuring the voltage and current, right? And then they are calculating the ratio. So the, let me tell you one thing, that voltage is measured by voltmeter, right? Voltmeter measures your voltage, or you can say it is potential difference, right? And these are connected in parallel also. And I will tell you about parallel and series combination later. And this is ammeter, which measures your current. It will measure your current. This ammeter will measure your current. So if V by I you calculate, you can find the value of R. So that is the procedure we'll follow. But there are devices such as multimeter to directly tell you the value of different distance value without actually showing you the voltage and current. So second point is what? Resistance is inversely proportional to cross-sectional area. That means what? Suppose this is a thicker rod and there is a thinner rod. You know that this cross-sectional area is like this and this cross-sectional area is like this. So obviously in this charges can flow more easily. That is, the current will be higher in this case and their current will be lower in this case. So you know that R is proportional to your I also. So if the current is less, the resistance here will be high and the resistance here will be low. Because there is more cross-sectional area, that means more charges can flow at a time through this cross-sectional area. That is why if area, cross-sectional area increases, more current will flow and resistance will decrease. Right. So from these two, if we assume that the temperature is constant, right? From these two, we came to a point and derived a relation for this resistance also. So I can combine these first and second, right? And I can write resistance directly proportional to length and inversely proportional to area. And since I want to remove this proportionality sign, that is, if I calculate L by A ratio in this x-axis and I want to plot resistance like this, L by A is increasing, resistance is also increasing like this. Okay, a combined effect of L by A I am taking. So to remove this, to get this value of R, we need to multiply something in L by A. And to remove that is to remove this proportionality sign. So I will remove this proportionality sign, and while I introduce a constant which is represented by rho, I will tell you what is this. So you need to remember this formula first of all, and this is nothing but a constant of, this is nothing but a constant, and rho is also a parameter, and it is nothing but rho. This symbol is rho, and we call is that the specific resistance of a material. So this is the property which is defining this your material case, right? It depends on the resistance of the, it depends on the material. Okay, so this is what resistivity will give you, right? That is the specific resistance of a material, that is at a particular temperature, what will be the resistance of that material. And in exams also, this specific resistance is asked. Define what is the specific resistance numerically. So if I want to define this specific resistance, I can see the formula. I can write like this. So you know that R is equals to rho L by A. So when I say when a material of length, let us say 1 units, right? And cross sectional area also, let us write cross sectional area CSA, okay, as 1 unit, right? As 1 unit only, or 1 square units, right? Then the resistance is called specific resistance. So meaning what? Suppose L and A, L I kept it as 1, A I kept it as 1. So this 1 by 1, that means R becomes equal to rho. So this now value of resistance will be giving your specific resistance, right? So I can also now write that the unit of resistance is this also from this formula, because units in competitive exams questions can be asked by twisting these units also. So rho L by A is what? If somebody asks you to find this unit of rho, you can see that unit of resistance is what? Ohm, right? And if area gets multiplied there, it will be meter square, let us say, right? And if you divide this length, it will be divided by meter, so it is ohm meter, right? What is the unit of a specific resistance? It is nothing but ohm, right? So this is the unit of a specific resistance, which is ohm meter, and you know what is 1. So this is all about specific resistance and specific resistance. And now one more thing you need to understand is that this specific resistance, it is a constant, right? You please keep this in mind. It won't change. Once a material is defined, once you say, hey, I am using a copper wire to make this complete this circuit. So once you have decided copper, this rho is fixed now. It is constant. It will change only when you change the material, okay, or you change the temperature also, right? So temperature or material you are keeping constant, then this specific resistance value is constant, right? And if that case you are considering, that is the temperature is also constant and the material is also same, that is rho is also constant, then the resistance will be depending on length and area only, right? Now let us discuss some question to understand today's concept, right? Let us say uh, current, a voltage of 4 volts is applied to a resistance of value R. The current flowing is 2 ampere. What is the value of resistance? So you will know if you need to find this R. So you know by Ohm's law V is equal to IR. So R is equals to V by I. So that is nothing but 4 by 2. So such that is 2 ohms. Such questions you can calculate easily. Now let me tell you a question also. This is important. A resistance R has a length L and cross-sectional area A, right? Now, if the length is doubled and the cross-sectional area is made 4 times of original, find ratio of old resistance to new. So these are the questions which can be asked in competitive examination also. So he is telling the resistance R has a length L and cross-sectional area A. So first of all, you know that let us consider the initial case as R1 is equals to, you know that first of all, you know that R is equals to rho L by A. Now we are seeing that if the length is doubled and the cross-sectional area is made 4 times of original, find the ratio of old resistance to new resistance. So one thing to be made sure here is that make sure is here is that the the material is kept the same, only length and cross-sectional area are getting changed. So this rho is still the same in both the cases, right? So let us consider when the first case was there, R1 was what? Rho L by A. Now in the second case, what happened? The specific resistance value will be the same because temperature isn't changed. If it is, nothing is mentioned, that means temperature is kept same. The material is also same, and the length is double. That means now the length has become 2L, and the area is what? 4 times of A. That is A becomes 4A now. So what is this? This is nothing but rho L by A and this 2 by 2. So 1 by 2, right? So we have found that R2 is what? 1 by 2 rho L by A, isn't it? I have cancelled this 2 and 4, right? So still you are getting rho L by A here. And what is rho L by A? It is nothing but the old resistance, which was R1. So I will replace it here. So R2 is 1 by 2 R1. Or he is asking to find the old resistance ratio to new resistance. So old resistance was R1, new resistance R2. So R1 by R2 is what? It is 2 will go there. So it is 2. That means the ratio of resistance is 2. All, or if I want to, so this is completes your question part. So what I want to say is, or you can write here, the question is complete. Now I am discussing it further, right? So you can see that from here, R2 is what? R1 by 2. Actually, the new resistance has become half times of the second. Why? Because the length was doubled in the new case, but the area was made 4 times. So you will see that as it is inversely proportional to the area, so area increasing is more as compared to the length. So that is why this cross-sectional area effect will dominate and the resistance will go down, right? So that is the meaning. So on and whole, the resistance is made half. So these type of questions are asked in competitive examination also, right? And some of the questions are asked using materials. So if they ask sometimes like, hey, with what material filament of bulb is made, then it is tungsten, right? And why tungsten, why this bulb material tungsten is used, we will be seeing in the later classes. But for now, let us summarize what we have learned today. We have learned what is current, right? Electric current, what is electric potential difference, right? Which is necessary for flow of current, what is closed electric circuit, and some of the symbols I will tell you. This is the symbol of a cell, you know. This is symbol of a battery, right? Cells in are connected, too many cells are connected, this forms a battery. Switch, I told you, this is the symbol of resistance, right? And switch also sometimes is represented as key. So this is your open switch or open key, right? Because in textbook it is mentioned like this, and this is a dot is there, then this means this is a closed circuit, then this is a closed, like this, right? So this you need to understand. So we have studied about electrical potential difference, what is electric current, and what is Ohm's law, right? Right, what is resistance. So this is what we have learned today, and we will be discussing about some of the questions also. If we, let us see if we will take some questions regarding to this resistance and Ohm's law together with the class itself, and in the next class, and then we will be seeing the combination of the resistance as well.